In this video, I'm going to go over the introduction to hypothesis testing with single sample. We're going to be going over the 4-1-1 basics of hypothesis testing worksheet. On this worksheet, if you go to the very last page or the second to the last page, we're going to be going over a question testing 30 cars. And this is what we're doing. So we have a total of 30 cars with rubber wheels, and we are comparing that to the population. And so just to kind of show you what we've got here, this right here is a car with rubber wheels. This right here is a car with plastic wheels. And so if we come up here, we are looking at the track time of cars with rubber wheels compared to all cars. Notice what I said there. We're not comparing rubber wheels to plastic wheels. We're comparing rubber wheels to all cars and looking at the finish time of cars with rubber wheels compared to the finish time of all cars. And so if you look at the rubber wheels, which everything up here is all rubber wheels, and then we can, let's see here. You didn't see it, but they all went down and they all finished. And so I'm going to do this again, but I'm going to do rubber wheels compared to plastic wheels. And I'll show you the difference. So we've got plastic, 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 and then we've got 3 with rubber. So we'll do rubber wheels right here, rubber wheels, and rubber. And then we've got 3 cars with plastic wheels, plastic, plastic, plastic. And so the question that we're having is, are cars with rubber wheels slower than the average, is the track time greater? In other words, are they slower? Does it take it longer to go down the track than the average of all cars? So ready, 1, 2, 3. And so all 3 cars with rubber wheels, turn this down a little bit. All 3 cars with rubber wheels went down and had a faster finish time than the cars with plastic wheels, than the cars with rubber wheels. But let's go ahead and I'm going to share my screen with you. So I'm going to, let's see, share screen. From beginning. Oops. Hold on. Let's try this again. Share screen, slideshow. Okay. And we're going to zoom, share screen again, share. Okay, so single sample hypothesis testing. We've got lots of different cars, and like I said, we're comparing the average speed of cars with rubber wheels to all. But hypothesis testing, what is hypothesis testing? Hypothesis testing begins with a hypothesis, a statement about a population parameter, and we're looking at, hey, the population speed of all cars. For instance, the mean speed of automobiles passing milepost 150 on the West Virginia Turnpike at 68 miles per hour. That's a population parameter. Hypothesis statement about a population parameter is subject to verification. So we're saying, hey, this is the average speed is 68 miles per hour. Well, we're going to test it and see if it actually is. The average cost to remodel a kitchen is $20,000. We can test that and see if it actually is. So there's a 6-step process, and we're going to be going through that 6-step process. And the purpose of hypothesis testing is to verify the validity of a statement about a population parameter, or like, for instance, we've got a population of cars with rubber wheels. And we say, okay, we've got a statement about a population of cars with, or a sample of cars with rubber wheels compared to the entire population. And we want to know, how does this sample or the population of rubber wheels compare to the entire population? And so we're going through a 6-step process to verify that statement. And so we're going to be looking at some sample evidence to do that. So First, we're going to state the null and the alternative hypothesis. So the null hypothesis says that there's no difference, or it's essentially the opposite of what we believe. And the alternative hypothesis says, hey, there is a difference. In other words, the alternative hypothesis, cars with rubber wheels take longer to go down the track. The null hypothesis, the cars with rubber wheels do not have any difference, or they are actually faster. And so we're going to show you how to do that. So the null hypothesis includes signs such as equals, less than or equals, greater than or equal to, but the null hypothesis will always have some sort of equal sign in it. The alternative hypothesis will not. So we've got the null hypothesis, the alternative hypothesis, and yeah. So the null hypothesis. We will be comparing the average finish time of a sample of 30 cars with rubber wheels. So notice all these cars in the middle, they all have rubber wheels. Something else that you might want to know is that these cars with rubber wheels actually cost anywhere from 5 to 10 times the price of the cars with plastic wheels. The cars with plastic wheels are normally about $1. The cars with rubber wheels are normally anywhere from $6 to $30 a piece. Which you're like, you spend $30 on a car? Not very often, but every once in a while. Those ones are like this one right here. This one was about $20 right here. So the one on the very far left, that Ferrari with all that detail on it. So the finish time of the sample of 30 cars with rubber wheels to the average finish time of the population. So in other words, we've got 30 cars with rubber wheels. You don't see all 30 cars, but the entire population is highlighted in blue. So we've got blue going all the way around. We've got the entire population, which includes the cars with rubber wheels. And so we're like, hey, are the cars with rubber wheels, is the track time greater, or the finish time greater than the population of all the cars? So once again, we've got rubber wheels on the right-hand side, plastic wheels on the left-hand side, but the entire population. So we've got a population of rubber wheels compared to the population of all cars. Okay, so the null hypothesis. Hold on. Okay, so the null and alternative hypothesis. Right here, we have the average finish time of cars with rubber wheels is less than or equal to the average finish time of all vehicles. So in other words, I've got the population or the sample of these 30 cars, and we're looking at, is it less than or equal to 3.45? What is 3.45? That's a great question. Well, let's take a look at your Word worksheet, and we will kind of work through this. Okay, so we've got this right here. What do I want to know? First of all, is the average finish time of cars with rubber wheels greater than the average finish time with of all cars? And then right here, what is the null and alternative hypothesis? So we've got rubber wheels, and then compared to all cars. So the average finish time of cars with rubber wheels is less than or equal to the average finish time of all cars. And then the average finish time of cars with rubber wheels is greater than the average finish time of all cars. And so that's what you would put right here. And so what is 3.45? 3.45, if you look at the prompt right here, we've got the average track time. You test a total of 30 cars with rubber wheels with the average track time. The known information from the population of all cars is that the average track time of 3.45 seconds with a population standard deviation of 0.2. From the sample of 30 cars with rubber wheels, the average track time was 3.8 seconds. And so we're going to get into that in just a minute. And so right here, we have the alternative hypothesis. The average finish time of cars with rubber wheels is greater than the average finish time of all vehicles. So average of cars with rubber wheels is greater than 3.45, which is the average of all cars. Okay, next, step 2, we're going to select a level of significance. In other words, I want to know how confident do I want to be? How willing am I to be wrong? It's also known as a level of risk, chance of type 1 error. And in other words, we normally use something, it can be any value between 0 and 1, but we normally use something like 0.05, 0.01, 0.1. 0.05, it's basically saying you've got a 5% chance of being wrong, or saying that there's a difference when there really isn't. 0.01, it's like, hey, you really want to be accurate. You only want a 1 out of 100 chance of being wrong. And 0.1 is, hey, you've got a 10 out of 100 or 1 out of 10 chance of saying there's a difference when there really isn't. So what does that really mean? The probability of rejecting the null hypothesis when it is true. So in other words, the probability of rejecting this null hypothesis, the probability of rejecting the idea that there is no difference when there really isn't, or the probability of saying cars with rubber wheels are not slower when they really are. So that's type 1 error. So there's type 1 error and type 2 error. Type 1 error is when you say your sample is equal to your population, but it really isn't. So in other words, you say, oh, the cars with rubber wheels are the same as the entire population, but they really aren't. Or the cars with rubber wheels are faster than the entire population, but they really aren't. That's type 1 error. Type 2 error is failing to reject the null hypothesis when the null hypothesis is false. In other words, you say that cars with rubber wheels are slower than the entire population when they really aren't. And so that's an issue as well. And here's a fun little chart over on the right-hand side. The different type of errors that you can make. So type 1 error, type 2 error. If the null hypothesis is true and you do not reject the null hypothesis, you made the right decision. If the null hypothesis is false, but you do not reject it, then you made type 2 error. If the null hypothesis is true and you reject the null hypothesis, you made type 1 error. And if the null hypothesis is false and you reject it, then you made the right decision. And so that's just type 1, type 2 error. To be honest, this is something that it takes a little bit to wrap your mind around, especially the way that you're supposed to say. You're supposed to say, type 1 error is rejecting the null hypothesis when the null hypothesis is true. It's a lot easier to say saying the cars with rubber wheels are not slower when they really are. Okay, so the null hypothesis. In the present example, we are going to use an alpha, or a chance of type 1 error of 0.05. In other words, there's a 5% chance before I ever get started. I'm saying, hey, I'm willing to say that there's a 5% chance. I'm willing to take a 5% chance of saying that the cars are slower when they really are not. I'm okay with a 5 out of 100 times. I would randomly do this, and it would give me that even if they weren't. Okay, so the average finish time of cars with rubber wheels is greater than or equal to the average finish time of all vehicles with an alpha of 0.05. And then the alternative hypothesis, once again, the average finish time of cars with rubber wheels is less than the average finish time of all vehicles, when it really, whoops, I've got those switched around. Hold on. Sorry, I had these symbols switched around on a couple slides. I just had to fix that really quick. But the null hypothesis is the average finish time of cars with rubber wheels is less than or equal to the average finish time of all vehicles. So that's the null hypothesis. In other words, there is no difference. And then the alternative hypothesis is that the average finish time of cars with rubber wheels is greater than the average finish time of all vehicles, with a 5% chance of saying that they're different when they really are not. Okay. Step 3, we're going to identify the test statistic. What test statistic should we use? And this is going back to the previous unit. Right now, we're going to either use a Z or a T. We're also a little bit later going to use something called a chi-squared. But we use a Z when we have the population standard deviation. We use a T when we only have the sample standard deviation. In this case, we do have the population standard deviation. The population standard deviation is 0.2. So because we have 0.2, we are going to use the test statistic because we have the population standard deviation. And so then we have to determine the critical values. So the critical values, how do we determine the critical values? Well, first of all, the test statistic Z is calculated just like what we did in Unit 3. We have the sampling error divided by the standard error. And so we're going to calculate that in just a minute, and we're going to get the actual z-score. But before we actually calculate the z-score, because that's going to be step 5 of the process, we need to determine the critical value. Okay, and we're going to do that in just a minute. But once again, we have the population standard deviation. Nothing really changed except we just put in the population standard deviation and we're using the z-score. But we're going to now formulate a decision rule. Okay, a decision rule uses something called a critical value. A critical value is essentially a point or a value that if your calculated value, if your z calculated value is above or below, or what I say, if your z calculated value is beyond the z critical value, or t or chi-squared, if your calculated value is beyond your critical value, you reject the null hypothesis. If your calculated value is not beyond your critical value, you fail to reject the null hypothesis. And so it's a decision rule. Before you ever take a sample, you make a decision and you say, if it's above this, or if it's beyond this, we're going to reject. If it's not beyond this, then we're not going to reject. Okay, and so it's a dividing point. So we have the ability to have either a two-tail test or a one-tail test. And we have a one-tail test. And the reason why is because we believe that it's going to be above or greater than. If we just said different, so the key word is different, a two-tail test, are cars with rubber wheels going to be different than than all cars, then it would be a two-tail test. It could be greater or it could be less than. And so there's a 5% chance of saying that it's different when it really isn't. In that case, we've got a two-tail test, and you've got critical values in the upper tail and you've got critical values in the lower tail. And so you've got the population mean, the population mean in the middle, which is that purple line. And then you've got the critical values on either side for a two-tailed test of that 1.96 or negative 1.96. Now, what's the probability of getting below negative 1.96 randomly? Assuming that there is absolutely no difference between the finish time of cars with rubber wheels and all cars, the probability of randomly getting a sample with a calculated value, calculated z value of below negative 1.96, the probability of that is 0.025. The probability of randomly getting a sample with a with a calculated value above 1.96, the probability of that is 0.025. And so you add those up together and it gives you a probability of 0.05. But because we have an upper tail test, we believe that it's going to be greater. We're going to put all of that in one tail. So what's the probability of randomly getting a value above 1.645? And that is 0.05. And so we've got our region of rejection, which is the probability of 0.05. Um, right here, there we go. The region of rejection. And then this right over here is the region where you fail to reject. The middle is the area where you fail to reject. So in other words, if you have a calculated value in the blue area, your z calculated value is in the blue area, you reject the null hypothesis. If your z calculated value is not in the blue area, you fail to reject the null hypothesis. And so, yeah. So right here, this is the decision rule. Before you ever get started, fail to reject the null hypothesis if z calculated is less than or equal to 1.645. Reject the null hypothesis if z calculated is greater than greater than 1.645. Sorry, there's a few things I completely redid this. And so there's just a few tiny errors that I'm catching as I'm going through this. But if z-calc is greater than 1.645, so the z-crit is 1.645, this is known as z-critical, and z-calculated, z-calculated. So you're comparing z-calculated to z-critical and z-calculated to z-critical on both of these. And yeah. So now you need to make a decision. So we're going to get our sample. We've got our sample of 30, and we're going to calculate a z calculated value and then make a decision. So we calculated, we got our sample of 30, and from our sample of 30, the average time was 3.8. So anything that is beyond that 1.645 is going to be considered statistically significantly greater than the population mean. So we have a sample mean of, or the sample of 30 gives us a mean of 3.8. And so we're going to calculate the z value just like we did in unit 3. We take the sampling error divided by the standard error, so 3.8 minus 3.45. So that's the sampling error, so that's going to be 0.35 divided by 0.2 divided by the square root of 30. And when you get that and you put it into Excel, it's going to give you something like 4.6 dot 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 e to the negative 22. What that means, I'm going to show you what that means. What that means is 0.14, 15, 16, 17, 18, 19, 20, 21, 22, 4, 6, 1, 6. Okay, that's what that is. The probability of getting this randomly is essentially this number right here. It's really, really small. In other words, it's this times 10 to the negative 22nd. It's the probability of randomly getting this is extremely low. And so we've got but let's talk about how we got that. First of all, we got a z-score of 9.585. So that was our z-score. 9.585 was our z-score because we took the sampling error divided by the standard error, and that gives us our z-score. Then after that, we calculate the p-value, the probability. And so the way that you calculate the probability, and I'm going to grab my Excel really quick. There's a few ways that you can calculate it. Okay, so we've got this 9.585. You can use a z-chart, but that's a pain. So I'm going to show you guys really quick how to do this in Excel. So the formulas are right here. If it's an upper tail, this is how you calculate it. If it's a lower tail, this is how you calculate it. If it's a two tail or a whichever one you use, whichever one is going to give you a value of less than 1 for this. But right here, this is an upper tail. And so we're going to do equals 1 minus norm dot s dot dist. And then we put in the z. And then we type in true for cumulative. Okay. And it gives us 0, which is unfortunate. But the reason why, if you were to do this negative, and once again, sometimes when you do it like this, here, let's do this. It doesn't always work exactly the way that you want it to. Oops. If it was negative, which because it's symmetrical, it would be the exact same. An upper tail would be the exact same as a negative a lower tail. So that's how I got this right here. But when you do the 1 minus, that's when it messes things up and it's like, hey, it's just 0. But it is essentially 0. So even if it gives you 0, it didn't give you a wrong answer, but we're not going to put 0 because the answer isn't 0. What we're going to do is we're going to put the appropriate notation. And so when you get something this small or you get a 0, you do the probability of randomly getting this is 0.001 or less than 0.001. Okay. And so there's 2 ways to decide on your whether or not you reject the null hypothesis. You compare the z, this right here, sorry, the z calc, you compare the z calc to the z crit, and because the z calc of 9.585 is above the z crit of 1.645, you reject the null hypothesis. Or you can compare the p-value of less than 0.001 to the alpha value. If the p is less than your alpha, which our alpha was 0.05. If your p-value is less than your alpha, you can also reject the null hypothesis. In other words, if p is low, reject HO is what it says. So we reject the null hypothesis because the p is low and also the z calculated is in the area of rejection. And so the z calculated is all the way over here. So we've got a z calculated of, let's do this, 9.58. So it is really far over. Oh, anyway. It's really far over here, so far over that you wouldn't even be able to see it. It's really far over to the right-hand side. So that's how you do that. But for step 6, you want to interpret, not just give the actual values, but you want to interpret it. Okay, we can conclude that the mean finish time. So what can you say or report about the test? Don't just report the z value, give the probability, give the mean, give all the information, so that way people can understand what you actually did. That the average finish time of 3.8 seconds for cars with rubber wheels is statistically statistically significantly greater than the average finish time for all cars. I'm also going to put n equals 30 because I want to say a sample of 30. The mean finish time for cars with rubber wheels is 3.5 or 0.35 seconds greater than the average finish time of all cars. And so I said how probable the results are. I gave the population standard deviation. I gave the sample size, and I basically said, based on all this information, we compared the z calculated value to the z critical value, and this was our interpretation. And there is a difference. And so that's how you would do a single sample test. We're going to be, there's lots of different ways to do a single sample test. I also want you to look at something, a resource that I put together for you guys, specifically to help you with critical values. So go to printable resources under unit 4, and we're going to go to critical values diagram. And with this critical values diagram, I'm going to download this so that way it's easier for me to see. Okay. I have the two tail, I have the upper tail, I have the lower tail, and for z values, they always stay the same. But then for t, which there's a whole nother lecture on t, it tells you, hey, this is how you do this in Excel to calculate the critical values using a t-score. And so I would highly suggest that you download this, print it. You can use this on your exam. And it also talks about, hey, this is how you write the decision rule. This is the region of rejection. And there's an entire lecture just over this. So I'd highly suggest that you download this and that you use it for your benefit. So that's pretty much what I got for the first unit, for the first lecture worksheet, and hopefully that was helpful.